All right, welcome back. This is multi-layer perceptron that we derived in the previous video. And as you can see that this is like a three-layered structure, a three-layer perceptron, also known as MLP. And it is in fact sufficient to fit any function. Because as we said in the previous video, we can have more complex target functions. And why are we just focusing our attention on XOR? Well, it helped us derive this form, but this form is largely sufficient for almost any target function. And we'll see how powerful this is in terms of like looking at the actual more complex target function and see how can we use this to fit that. Well, in general, in most cases, we don't need deep networks. What does deep network means? Like more layers. Deep means more layers. So deep is more layers, and then we can get away with a wider network with the same number of layers. So wide means more nodes. And we'll just now see how is that. So here we are saying that more layers will allow us to, of course, implement F, right? And the more layers we add, we can get like more flexibility in our model, and those layers, those additional layers are known as hidden layers. So of course, the possibility of adding more layers is always there, but in most situations, we can get away with a wide network itself. And we'll see like theoretically speaking. However, going back to what we said, we are going to prove in this video is the rule of universal approximation. Let's see what that is. And so the rule of universal approximation states that any target function f that can be decomposed into linear separators can be implemented by this three-layer MLP, or the multi-layer perceptron. And of course, this can be proven analytically, but we are going to prove it by using a picture because that's more relatable in terms of what's going on. Let's look at this more complex target function. So let us assume we have this two-dimensional plane and we have this circle as my decision boundary, such that everything inside this is positive and everything outside this is negative. And so we need to come up with some hypotheses in terms of the perceptron. Of course, by looking at it, you can tell that a perceptron will never be able to like fit this. But we can look at like multiple hypotheses, just like we did with the XOR. So let's come up with something here. And the most logical thing that I can come up with is like, why not just put it inside a box, right? So this is my H1. Everything in this side is negative and this side is positive, right? And then maybe my H2, right? Call this H2. So again, everything here is positive, the other side is negative. And then maybe this is another perceptron, H3, and everything this side is positive, everything this side is negative, and another one that just like touches, kind of tangent, and H4. So I've come up with 4 hypotheses to capture my target function, which is a circle. And well, I can get the final output such that everything inside this, like when they're like all 4 of them are combined, everything inside is positive and everything outside is negative. And we can use in like the AND function to get the positive region. But notice that we'll still get errors in some of those small regions. For instance, this region here, and this region, and this region, right? Although it's negative, but I'm going to get positive because this is how my perceptron is capturing that. So while we can say that, how about adding like more single like perceptrons to capture like and get rid of this? So we can definitely do that. How about we have some kind of these like structures that somehow go tangent but also kind of cut through this. Cut here and also cut here. So they're like going to, and this by the way should like intersect. That's what I meant. This is not the right line, right? And so this by the way is going to reduce or like get rid of a lot of this region, as you can tell just by looking at it, because it's going to be tangent there. But then it has its own like error terms somewhere added here, like little bit, but like not huge. But of course we have these error terms. So these are smaller error regions, but of course, let's say we are not happy with this, so we can add more lines. Let me add 4 more lines and be like somewhere in between this one and this one. And of course, I'll be like really bad at drawing those, but you can imagine that I can draw like 4 more perceptrons. And so basically I can get 16 perceptrons to almost capture this function. So we'll have like 16 nodes and one and of course, like if we had multiple positive regions, then like I might need more layers and more perceptrons. But in this situation, I can somehow get within a good approximation. So all we have done here is that we are trying to cascade linear perceptrons like with 3 layers such that, let me show you what's going on. So first of all, this is the universal approximation I'm talking about. A sufficiently smooth separator can essentially be decomposed into linear separators. What that means is if I have many of them, as you can tell here, 16 of them, then I can somehow model this. And how am I going to model this? The way I can model this is using the MLP in such a way that the first layer will be the number of perceptrons, which in this case is 16. Let me show you what that means. So this is my first layer. This is my input and this is my first layer, right? And so this can have like 16 nodes instead of 2 plus the augmented one. And then the second layer of ANDs like will be the nodes will be decided based on how many positive regions do I have, just like we did with the XOR. And then one final big OR. So you can tell that just by being able to come up with these linear separators or these perceptrons and a combination of these, I can still use my MLP to get what I want, right? And so that was like an example. That was like a proof by picture, of course. And let's see what are the observations. So the first observation is that we can cascade linear perceptrons with 3 layers, like add the numbers to the nodes, right? The second thing that we are noticing here is, and if I have like space to write it down, the second thing that I'm noticing here is that the ability to set the weights on each perceptron that we have, right? And this might only be required in the first layer that defines the perceptrons, because the second layer is computing ANDs and the third layer is computing ORs. Okay, so what exactly am I saying? I'm talking about these weights here, right? And so we need the ability to set them, because after that it's the ANDs and the ORs. So that is giving us like some flexibility with the weights, but not quite here, because I know that this is an AND and this is an OR. So what can I do there? Well, I can extend or I can add on my fitting power or my approximation power by relaxing this ability so that I'm also able to update the weights in the second and the third layer, right? Why am I not letting myself do that? Well, this is going to give me a huge amount of fitting power. Agreed or no? Yes, it is going to give me a lot of, like, if I relax the ability to update, and update, by the way, I mean I can every layer, update weights in every layer, that can give me a very good, excellent, in fact, approximation power. So why am I not doing it? Well, this comes back from the theory, and the theory tells us generalization is going to suffer. Generalization is going to be affected because it's not just the fitting power that I'm after, but also how well my model generalizes. So generalization will, or may, I would say, may suffer. And we have a whole lot of discussion on this later on. But the fact that we cannot escape theory here. So the more flexibility you add in terms of the nodes, in terms of the weights, you are allowing more positive regions. Approximation capability is going up, right? Let me write it down. Approximation going up. Generalization most likely going down. And we can use the tools that we already formulated earlier in our foundations here as well, right? And we will be using them, of course, because like the question of overfitting has its own set of solutions, and we will bring them in, but not just yet. Okay, it's enough to know that we have this situation here that we need to deal with. So now the question arises how to set weights, because here for analysis purposes, I did all of this because I'm just like assuming that I know like my target function f, but obviously I don't know my target function f, right? I just have the data. So how do I get the weights? Like I have the data only and I have to fit the data. So even for a simple perceptron, if you remember, like for the perceptron in chapter 1 or 2, I don't remember exactly which one, we had these algorithms depending on the problem. For example, the classification problem, we use the PLA and the pocket, right? And then for linear regression, we had the pseudo inverse, right? And for the third one was logistic regression, we used the gradient descent. All these were there, and of course, you can always argue that we have them here as well, right? But now imagine these multiple layers of the perceptron and the interdependencies amongst them. So what is this? This is really a hard combinatorial problem, if you think about it, because my original perceptron, when I'm trying to get like 0 errors with the PLA, even that was a combinatorially hard problem. And so what should we do? Well, that's fine. But because this is a hard problem to solve, given all the interdependencies and so much like these layers and nodes all working together, this motivates us to derive something that makes this like MLP representation simpler. Because now we have like these weights and we have like some restrictions in here, and we have the sign function. More importantly, we have the sign function. And if you remember, the sign function is non-differentiable. It's more like a step, right? And so we cannot apply many of these algorithms that I just like stated here, especially like the gradient descent, which is like one of the most useful ones. And so what should we do? So what we are going to do going forward is we are going to replace the sign function in my MLP sign function with something that's smoother, that's differentiable, and then that's easier to use in these algorithms. And that's known as the sigmoid. All right, so when this change happens from the sine to the sigmoid, and more specifically, most of the times we use tan h. Of course, there are other functions available as well. Then the MLP converts to something that's known as the neural network. That's the neural network, at least in the current form as it is being used. All right. So now what we're going to do next is we will build some notation today and talk about the model in the next lecture. Why?